Not.
Anyway, join me in welcoming Andy Ruina.
Complicated pun. I meant to be alluding to Kevin Lynch, not the action of lynching. Thank you for having me here. Before I give the talk, if I subtracted from the talk all the things I learned from people at Carnegie Mellon, and all the things that were done by people in my lab who are now at Carnegie Mellon, the next thing I would be saying is, thank you very much. So in a way, I have nothing to tell this audience if I add up the different pieces. I hope I have something to tell different people, others of you in the audience, different pieces. So the basic question I want to talk about is how might people be controlling their walking? And I'm not so deep into this as some other people who are in this room. Or how should we control robot walking, which maybe I'm as deep into as some other people. And the big things about, say, walking robot is that you don't want it to fall down, and you don't want it to use a lot of energy. Then the acknowledgments here, A, B, and C are professionals who've had big influence on me. B is students who've been in my lab, and C is people who've given me money. Okay, so what's the problem is robots use too much power. If you take other robots besides ones from my lab and look at their cost of transport, which is a dimensionless measure of how much energy they use, which is the power divided by weight times velocity. And that's a natural scaling because certainly it's harder to move more stuff and it's harder to move faster. You could also say this is energy used per weight times distance. So it's a natural dimensionless measure of energy effectiveness. The cost of transport for people is on the order of 1/10. Maybe it's 3/10. And for typical robots, it's in the order of 10. And maybe that's 2 or 50. But there's a disparity of something like a factor of 100, which maybe is a factor of 10 or 500. But there's a big disparity there. And then the issue is that robots, as a rule, are too touchy. And the main measure of that is what I call the Atkinson index. Chris is not here today. But the Atkinson index, we had a long discussion at a robot meeting about how do you measure the stability of a robot. And people had all kinds of ideas about eigenvalues and this and that. And Chris Atkinson raised his hand and said, I know what it is. He said, look at the demonstration of the robot. Look at where the person who made the robot is. Look at where the robot is. Measure the distance between the two of them. If that's small, the robot is not very stable. If that's big, and I think that's really a better measure than anybody else has cooked up. I think of it as like comfortableness or reliability. If we take this group of people and we all walk out after this talk, you're not nervous about anybody. You're not thinking, oh, I hope nobody falls down on the way out of this room. But if this was a room full of robots today, you would be standing far away, not because you trust them, but because you're afraid of them. So the famous robots to compare against are Petman or Atlas from Boston Dynamics. And here's a video from the web. And I don't know how to hijack videos from YouTube, so I got to show you this from the web video. And this is actually, I mean, you can't complain a lot about this robot, except for that it's not doing too well on the Atkinson index because of that red cable there. It's like got a big safety line, which probably that line's been there since Ben Brown was working on these robots 30 years ago, right? So it's rare that they're, now Big Dog now is taken off tether and is doing pretty well. And then the other famous robot is this Asimo. Now Asimo, I've been talking about robots for a few years now. I always used to show Asimo videos to just make fun of them. But recently, I can't really do that anymore because Asimo is getting pretty good. So now the only thing I can make fun of left is, I mean, you could argue about whether it's natural or not, and the bent legs are a little funny. It looks maybe a little tiring for a person to run like that, but it's running very well. They're not hovering over it, though part of this Atkinson index has to be how belligerent the demonstrators are feeling, how much it matters to them, to how much big a chance they're willing to take. So I don't really know how much they trust this robot, but it looks like pretty much it did this pretty well. Still, as best I know, the energy use, even if it is comfortable, reliable, which I'm not sure it is, you can't tell from limited videotape, but even if it is, it's surely using 10 or 100 times as much energy per weight and distance as a person is. Okay, so that's the challenge. There is a solution, which I've been working on with a biologist, which is to make explicit use of neural networks, reinforcement learning, genetic algorithms, and evolutionary optimization. And we've done pretty well at getting this to work for walking. And here's sort of early results along this line. And it's very reliable. 14 years later, it's still walking. So, say again?
What about the
The
outtakes?
outtakes on this one, well, I mean, they're good, right, on this one. This deep use of neural networks and reinforcement learning and genetic algorithms and evolutionary optimization actually works very well. But let's say you don't want to add to the world's population and you want to make walking things. You do this trademarked bio-robotics. Howie Choza told me today he's trademarked this word or registered the domain name. But so what? Okay, so biorobotics.choza. But you think of animals as machines, use machines as models of animals, kind of engineering approach as opposed to mechanical engineering approach as opposed to worrying about emotions and things like that. Okay, so what am I going to talk about? The talk basically is two parts. It's passive dynamics are great, and then part two is passive dynamics are terrible. So let me sort of go down that line. So what are passive dynamics? The word passive means sort of does its own thing. And what do you mean? Everything does its own thing. We live in a universe, and the universe is doing its own thing, and we're just part of it. But you sort of divide up the conscious world we live in and think if it doesn't have motors or muscles, but maybe it can fall down. There's gravity, and it's not controlled by nerves or electrical wires. And then dynamics means it moves, like it obeys Newton's laws. And the passive dynamics takes inspiration from three places, at least to me: bicycles, the Wright brothers, and toys. So let me start telling that story. So the first is that bicycle balance. Bicycles balance. Here's a bicycle balance. There's a front wheel, which is, I should use the pointer. There's a front wheel, which is a very broad wheel in this case, and a back wheel. And this bicycle is stable, and is stable because the radius of curvature of this thing, the center of this circle in this direction, is above the center of gravity. And when people talk about bicycle balance, or when I talk about bicycle balance, I'm not really talking about that. I'm talking about a bicycle with narrow wheels which can balance itself. And so how does that bicycle self-balance look? To start with, there's this motorcycle self-balance. So here's a motorcycle race. This is like the kind of thing that probably lots of you do on your spare time is look at weird things on YouTube. If you pay attention here, you'll see that the people fall off their motorcycles. This motorcycle is separated from its rider, and it goes on and on. So that thing that motorcycles do, it's got a name. It's called ghost riding, and there's probably, I don't know, hundreds of videos of ghost riding on YouTube. And there are tricks people do riding motorcycles. They ride their motorcycle, they jump off, and they run next to it, jump back on, and things like that. There's bicycles do the same thing. And here's a bicycle, and it can balance itself pretty well. So this has been known. A known feature of bicycles probably since about the 1870s, but certainly it's written really clearly by the 1890s. And not only that, people have wrote equations which are pretty good models of this. And what's the basic idea is here, which you can see if you knock the bicycle sideways and then watch what happens. When it falls to the right, it leans to the right. When it falls to, if it falls to the left, it steers to the left. It falls to the right, it steers to the right. And that's the nature of balance when you have a small support. It's the way you balance a broomstick on your hand. When it falls to the right, you move your hand to the right. And the bicycle does this by itself. And why it does it by itself is another whole story, and how and so on. And I talked a little about that earlier today. I'll get back over here. So bikes can do this thing. Is it part of bicycle design, like maybe we want to think of robot design, that robots could balance themselves? It's not known whether bicycles were designed this way on purpose. I think, as best I can, nobody knows this. So it was part of bike design pretty consistently starting in the 1890s. For example, here's a bicycle built in about 1900 by the famous bicycle designers Orville and Wilbur Wright. Everybody knows who they are, right? Famous bicycle designers. And here's a motorcycle, which looks very much like a modern motorcycle from the same era by an equally famous motorcycle designer named Glenn Curtiss, who's known for buying out the Wright brothers, making Curtiss-Wright Aircraft, which was the biggest airplane company in the World War II era. So I was foreshadowing the airplanes which are coming up, but so the airplane makers obviously were interested in bicycles first, like any person interested in dynamics should start with bicycles. So people can ride on a bicycle, but bicycles can ride themselves. First, there's some interesting, yes?
Side question about bicycles.
Yes, please.
So back in the 1800s when they were doing those equations for bikes,
Yes.
they were much different. It was Orville Wilbur's new bicycle that gave rise to the modern bikes.
Yes.
So could you push one of those big-wheeled bikes and have the same stability?
I don't know about the big-wheeled bikes. But the bikes actually, if you go back in time before the big-wheeled bikes, they looked like the newer ones. So they went from these two equal wheels up to that funny design and then back to the two equals again. And back when they were two equal wheels, there's some indication that people had some sense that they could balance themselves, at least that they could ride no hands. And those big-wheeled ones I don't know about, the penny farthings. The big wheel was about getting bigger gears without gears. So it's just the big wheels. The evolution of the big wheel is just trying to go faster with a given size crank. So there's interesting, bicycles are interesting sort of from a technical point of view because without friction or dissipation, they can balance themselves. The last time I gave a version of this talk, somebody went grumbling out of the room, where's the math? So I've added some math, which is this in the form of words here, which is you can write differential equations and you can calculate eigenvalues, and for the right model, the right bicycle, the eigenvalues have negative real parts. They're math. So now let's go back to this idea that we get. You ride a bicycle, yet a bicycle can balance itself. So now think of yourself as a walking machine and detach your brain from your body. You are riding your body. Here's a machine. It's a bunch of sticks and hinges, just like a bicycle is a bunch of sticks and hinges. And maybe you can walk in your body, but maybe the body can balance itself. So that's inspiration number one from bicycles. I mean, if you didn't know about a bicycle ahead of time, it seems implausible. And maybe this seems implausible to you unless you know the story already. But I say it's no more or less plausible than the bicycle story. Okay, second inspiration is airplanes and gliders. If you take a little model airplane and throw it, it can balance itself. This toy plane demo is for the paper airplane model I forgot to make, but there's paper airplane, throw it. When I was in 8th grade, I won a paper airplane contest. The Wright brothers developed a glider before adding power to their plane. And they said, hey, look, these people are putting motors on these things. That's too complicated. Let's start with a glider. And some people credit their success by not going whole hog right at the beginning and putting a motor on. And here's a letter from Wright to Octave Chanute. who was a famous bridge designer who went into airplanes after that. He said, the flight of the buzzard and similar gliders, by sailors in his gliders, is a convincing demonstration of the partial needlessness of motors. So this is in 1900, a few years before they got to powered flight, which is 1903. So the Wright brothers developed a glider. Now you can think of what is a motor. Well, a motor on an airplane is a propeller. What's a propeller? It's the thing that pushes. You have an airplane, and it can glide down like this with gravity pushing this way. Now you take this picture of the airplane gliding down and rotate the picture, rotate the gravitational field, and you have an airplane flying like this. This is the same glider, just looking with your head tipped, if you like. Now take this crooked force and replace it with a vertical one and a horizontal one. It's mechanically the same. Now take that horizontal force and make it come from a propeller. So that a glider, if you can make a glider work, then you can make a level flight work by just putting a force at the center of mass of the rigid airplane from the propeller. So it's totally natural to say, I know how to make a glider work. I'm going to add a motor. It's got to work. And that's what the Wright brothers did and said. So a few days before they put a motor on the airplane, one of them wrote to their sister and said, we're going to have powered flight. And the first day they tried it, the motor broke. But the next day they tried it, it worked. And that's like the famous picture, one of the most famous photographs ever taken, is they just threw a motor on a glider and it worked. And the reasoning, I think, is tight and correct. If you can make a good glider, of course you can make a powered airplane work, because it's just a different way of rotating the gravity field. I don't think that was their language. So the inspiration is airplanes. We're working our way up to walking robots. Build a glider first, then add power. The idea is make a robot that can walk downhill like a glider, then replace gravity with motors, and you have something walking on level ground. And this pretty explicitly, at least this was my understanding of what inspired Tad McGeer. And I think Matt says you were present at the first time Tad McGeer showed one of his robots in public. I think I heard that from you. No? What?
Some other man.
Are you sure?
No.
Now the mechanics here isn't quite as tight as for the airplane, because the airplane is pretty clearly close to a single rigid object, and maybe a walking thing has lots of parts, and to actually think of walking on level ground as being a rotated gravity field, you'd have to put horizontal forces at the center of mass of all the links of all the parts. But maybe if you're just losing a little bit of energy, it doesn't really matter where you put in the part that's lost. Just like when you have a vibrating system and there's a little bit of damping, it sort of decays the same way. It doesn't much matter where the damping is. Do the backwards of that. Okay, so that's the second inspiration. The third one is toys. This one on the left is called the the Wilson Walkie, this little penguin, patented in 1938. Tom McMahon had a version of this toy when he was a kid. Tom McMahon's a famous biomechanics guy who was at Harvard and has since died. The idea of walking toys goes back to 1888. This is the oldest patent we found. But the name on this patent is, quote, an improvement on walking toys. So presumably the idea goes back older than that. And these are little walking toys which walk on their own. Let me show you how that looks. Here's the wire walker. This is a reconstruction of it that was made in Delft. I have a few of these wire walkers, and no one in my lab has actually gotten one to walk, which is an important message, but somebody in Delft was patient enough to get it to walk. Actually, the first one I got was mailed to me from someone in Romania who made it for me, and the postwoman came to me in my box and delivered this thing, and she said, I hope this isn't anything delicate, and she delivered me this cardboard box which was squished flat. Bend it all back together again. That's walking down a slope, yes. Or it's walking on level ground with thrusters acting at the center of mass of each of the links. Special gravity thrusters. And here's the penguin walker. This is one that you can buy on eBay. Lots of people had this toy in the 40s and 50s. It's not the kind of toy that could be popular now because it's a little too fussy, which is important also. But Tom McMahon had this as a kid, and it inspired him to think that maybe walking is something like this. And he and a student, Simon Mochen, did a pendulum calculation, and their model of human walking was as a stance leg, a thigh, and a calf, and they looked at this triple pendulum. So a triple pendulum, they wrote Lagrange equations, they calculated the motion of the triple pendulum, and they saw that in the swing phase, the motion of the links of a triple pendulum was like what people did when they were walking. Okay, so the idea, C, is let's make robots that are like toys, and then, like the Wright brothers, add a motor and make it work. So this started with Mochen and McMahon. Tad McGeer, who was an aeronautical engineer, all ties back to bicycles and airplanes, you see, said that's a good idea. He was inspired by this Mochen and McMahon paper and by these toys, which had inspired Tom McMahon. Similar things were done by Formalsky in Russia. But I don't know exactly what he's done. None of his papers are translated into English, but I've seen him speak on these things, and he clearly had these ideas before McGeer did, many of them. And McGeer is and was an aeronautical engineer who was explicitly inspired by the Wright brothers. So let me show you some videos of passive dynamic things. First is a Cornell copy of McGeer's walker. So the design of this robot is straight from McGeer. We changed some details, but they're only engineering details, like the sizes of bearings and things like that. This is sticks and hinges walking downhill. This end of this ramp is lower than that end of the ramp, so it's walking down a slope of a few degrees. It is just gravity pushing down and slightly forwards on the center of mass of each of the parts relative to the level ramp, or on the crooked ramp is pushing down. This thing has a life in simulation, so it's got sticks and hinges solving the pendulum equations and the collision equations and so on. In McGeer's world, when he first did this, it had a life in simulation first, and then after he got the simulation to work, he built the thing. And there's a video I'm not showing, but of McGeer, the first time a device of this type worked, and Tad McGeer goes and giggles. It works. Like, the calculation was right. Yes?
So would you agree that the slope of that is equivalent to the coefficient of transport?
Yeah, so the slope here, and whether it's the sine of the slope or the tangent of the slope or the slope, small enough so it doesn't matter which you pick, is the cost of transport. So this is a very small, like 0.05. So it's about 4 or 5 degrees. Okay. We built a few of these at Cornell. Then we went on and tried to do more fancy things. So the next one is trying to make it look three-dimensional. And this is Steve Collins making this robot go. Here's the first version. And this morning, Steve told a story about this first version. I never saw this first version work. It walked twice, and one of the 2 times was that videotape. And I never saw it. So Steve came to the lab as an undergraduate. This is Steve here in the front row, mechanical engineering at Carnegie Mellon, and added arms to this and got it to work, reliably in a way. So if you watch, say, this video, I don't know, one of these videos, Steve very cockily keeps the videotape running while he picks up the robot and moves it to the top of the ramp again, and to say, see, it can work twice in a row, sometimes. Now, if it works 1 time out of 5, he only has to try those double takes 25 times to get a 50% chance of getting it to work. But so it was reliable in the sense that lab demos were functional sometimes when Steve was there to give them. Right now, this robot is in the lab, and no one can get it to work. But this is, in terms of the subject of passive dynamics, I'd say this robot is kind of the pinnacle. It's the most lifelike, complicated robot. And I say until the most recent videos of Petman and Atlas, is perhaps the most sort of lifelike walking of any powered or unpowered robot. At least I look at it and see it that way. But now, I'd say just for the first time in the past year or two, there are powered robots that can compete with this in terms of sort of looking natural. So any questions about this robot? Yes?
Is there something about the shape of the foot? It looked like it was rocking, but then when you get a close look, it looks like it's staying in contact. Is there something cute about the...
Well, there's stuff that we thought was really cute, but I'd say the depth of our understanding is marginal. But we had thought we want to take a two-dimensional concept and lift it into 3 dimensions, kind of. We don't want it spinning around, steering and yawing, so we'd like to have some extended contact. So we'd like, when each foot is on the ground, there are 2 points of contact. So that means we want, but on the other hand, feet are moving from the right to the left, and the center of mass is going in an S-shaped curve. So if we take a given shape of curve of the center of mass, we can calculate a center of pressure position, and we try to put that between the 2 rails so both rails will stay in contact. On the other hand, the shape, assuming they are in contact, the shape of the rails determines what that S-shaped curve is. And Steve and I went back and forth doing pencil and paper calculations and estimations and tried to make that all just right. But when you look at the video, you see it rides up on one rail or the other, and it didn't work anyway. So probably the main thing that makes this work is compared to the unreliable previous version, is that it's got these counter-swinging arms, so there's not a lot of twisting going on anyway. Our intention was to have these 2 rails with 2 careful curves that made the center of mass go back and forth just right, so there'd be 2 points of contact at all time, and it wouldn't twist, but I don't think we achieved that. Does that address your question? What? Say it again, Steve? It's a ZMP controller without a computer.
Exactly.
Okay, so then I say academically, the most interesting robot we've made is this one. And this is big science. It'll cost you about $20 to reproduce this, but you can make 4 of them for $20. You have to buy the whole kit. It's made of Tinker Toys. So inspired by bicycles explicitly this time, I thought, hey, bicycles can balance themselves when they're moving, but not when they're stationary. Can we test this passive dynamic walking robot idea and see whether we can make a passive dynamic robot that can balance itself only when it's moving? And you say, well, robots are different than bicycles because robots don't have fast spinning parts. And that's true, but at that time, we knew that you can make a bicycle that doesn't have fast spinning parts. For example, this one has no gyroscopic effect that can balance itself also. This has effectively ice skates for wheels. It has counter spinning front and back wheels, so there's no angular momentum. Now, at this time, this machine hadn't been built, but we knew conceptually it was possible to make such a bicycle. So bicycles, even without spinning parts, can balance themselves. Is it possible to make a robot without spinning parts that can balance itself? Well, obviously, we've done that, and the toys did that back to 1888. Can we make one that cannot stand up? Well, then there's technicalities about what you mean by not stand up. The McGear robot with the inner and outer legs could stand up like this, but the feet were small enough in curvature so it could not stand up like this. So the challenge I gave to my student, Mike Coleman, was can you make one that can't stand up in any configuration, so even when the legs are splayed. And so this one, even when the legs are splayed, you can draw a line sort of looking down the contact line, and there's a center of curvature which is below the center of mass in this case. So this can't stand up any which way. And just for graduate students thinking about their careers and so on, Mike worked on this for about 3 years in simulation. And the smallest eigenvalue you can get, see there's math in here, was 1.15. Now in this world of Poincare maps, instead of continuous differential equations, you want eigenvalues inside a unit circle, less than 1 in magnitude, and he could only get it a little bigger than 1. So we decided that his PhD thesis was, it seems like it's impossible to find a passive dynamic walker that can't stand up. And a few days before his thesis defense, he decided to build a little Tinker Toy model. The purpose of his model was to show the mass distribution that all his optimization showed should almost work, eigenvalue of 1.15. And then he did this thing, which I don't know why he thought to do this, but it's just meant to be a conceptual model. He tried it. And then it did walk. And then it took 2 more years. for the computer to agree that it could walk. So it's a little bit fussy. In fact, it's extremely fussy. It's very reliable, like the other robots are. Very, very reliable on videotape. Just walks again and again. Okay, so Steve, same guy, Steve here, said, I want to power a robot. And lots of students in my lab wanted to add power to robots. And I said, we're the passive dynamics lab. Everybody else is powering robots. We've got to find out what you can do with passive dynamics. And he said, I really want to do it. And I thought, well, you got that other robot to work. I sort of gave him permission against my better judgment. And he tried to do the Wright brothers thing of take that two-legged robot and add a little bit of power and get it to walk. And this is Steve with that robot. So now the ramp is not sloped downhill. It's on level ground. This is conceptually the same machine, only it's got a little bit of power. What is a little bit of power is that it's got a little electrical switch here, like a 50-cent switch. It's half falling off because the electrical tape is it's falling off. It's sticking on this. When the switch gets triggered, it lets a little thing release, which releases a spring, which does a little ankle extension. So there's something like 60 lines of code running on a teeny microprocessor that's acting approximately like a few relays and timers. One foot hits, the other one triggers, and a motor winds up, gets ready for the next one, using a mechanism that we basically copied from Ben Brown. So everybody's here, right? The mechanism inside this, I've told you this before, right? It's sort of copied from the bow-leg hopper mechanism of sort of winding up between and then triggering and releasing. Okay, so this is typical videos of this robot walking. What I mean to say, this is all of the videos of this robot walking. We have hours of video of this robot falling. Steve was meticulous about videotaping himself when this thing was falling down. And maybe this is maybe not exactly typical, but really how this robot works is like this. So this is Steve. At this point, he's a first-year graduate student in Michigan who came back to Cornell for the summer to work on this. So, and you watch this video. You want to look at this point right up here in this video. This is where the action is. Got to slip the sheet here a little bit. There's smoke coming out of the processor. So that's something like a month, right? Disappeared just like that. But we have, I don't know, something like 100 videos of the robot falling down, usually not so badly. But that's the nature of this thing, which I will explain a little bit more what I think the messages are. Just to show you sort of a fun video, I gave another guy a challenge, no thanks, of making a hopping robot that could not stand up. And this is a optical equipment designer. And he sort of took the challenge and worked on it and made this hopping robot that can go down this ramp without falling down. This is a beautiful machine. This guy's name is Peter Steinkamp, and if you go on the net, he invented a bunch of little hopping robots. Play, man. This is a slow motion video of this one. So this cannot stand up, and it can hop the length of a ramp. It can do 100 hops in a row. It can do that many times in a row. It can hop 100 times down a 16-foot ramp. And the computer thinks it can't. So this is still in the stage that Tinker Toy was in. As far as the computer says that the smallest we can get the eigenvalues as like 1.02. So the theory we have seems to trap this thing away from being actually dynamically stable. Yet it can do, in practice, 100 hops. And our way of reconciling that is that we think the actual physical robot is marginally unstable, probably, and that people have learned to launch it very well close to the periodic fixed point, and that there are little tricks that give you feedback when you launch it to help you find that fixed point. Because we match so much about the motion in simulation. For example, it has a period 11 oscillation, period 11, and we catch that in our simulation as well as in the robot. Now, Peter Steinkamp is a guy who sees passive dynamic robots wherever he goes. And so he was unpacking a refrigerator one time, and he thought to himself, maybe this piece of packing foam is a passive dynamic robot. And it was. Somewhere, no, this is a disaster I've never had before, but I think my power cord is in my last talk. Oh, no, here it is. No, I got it. I got it. Well, somebody help me find an outlet just so I'm not distracted by this.
Right in the front here.
I'll
There in the front. That black.
Okay. Okay, so that's passive dynamics. What are the morals here? The Collins robot, is robust and walks every time on video. Actually, it doesn't, right? That's what I showed you, Steve's Bad Day. I won't tell you the real name of that video. What's the problem? I feel like for the many years I worked on this passive dynamics thing, I misunderstood the whole Wright brothers thing. So I now want to tell you what my misunderstanding was. Let's start with that first quote I had of the Wright brothers. The full quote is, "The flight of the buzzard and similar gliders is convincing demonstration of the value of skill in the partial needless motors." And it continues, "If it is possible to fly without motors, but not without knowledge and skill." So what the Wright brothers were doing wasn't mastering gliding first and then power. It was mastering control first and then adding a little power to show people that they had mastered control in a way that was useful. So it's a different analogy. Passive stability, as far as I know, wasn't part of the Wright brothers' considerations at all. When they thought about bicycle balance, which they did a lot, they were obsessed with bicycle balance. They were obsessed with how bicycles are controlled and balanced, not with the passive stability of their bicycles. So I don't know, maybe other people know more, but I know nothing about any interest of the Wright brothers in passive stability. Everything was about control for them. Later on in airplane design, people talked about passive stability. Okay, so what are some thoughts about this? If you take a passive dynamic robot that barely works and you add a motor to it, you get a powered robot which barely works. So this whole inspiration of passive dynamics doesn't take you very far. What do you think about the biological analogy? When people walk, they use sort of remarkably little muscles. You look at what leg muscles are used when, and the muscles are off a lot of the time, as witnessed by the fact that Tom McMahon could do that triple pendulum calculation, and the way the legs swing is very much the way a passive pendulum swings. The muscles are mostly off. But it's not like God, nature, put human bodies down and then said, let's add a little bit of muscle power. The evolutionary history is that we had very evolved control systems when we were worms. And bit by bit, our bodies got more and more complicated, moved to higher and higher Reynolds number, moved to maybe more and more unstable configurations, all with the control system well evolved. And maybe not evolved in every detail, but the capacity to deal with complicated mechanical systems. Another mistake is this idea that minimal use of motors, which you see in people walking, implies minimal control. Just because you're not using things very much doesn't mean you haven't mastered the situation. So you imagine, a dressage rider or probably the coach of a baseball team or a football team, just little commands at the right way and the right time make the system work well. We had thought that a key feature of a plant, airplane, bicycle, walking robot, is that the plant, the machine, be self-stable. And probably, I think now, the real thing that's important is that the plant be controllable. And what do you mean by controllable? There's a technical definition of controllable in control theory. I don't mean quite that. I mean that there's enough control authority and fast enough response time and accurate enough sensors to be able to control the robot, which in this case means that if you have a system with delays, it is difficult to control something which is unstable in characteristic time smaller than delays. Not impossible, but the longer in time you want to be able to control something longer than a characteristic instability time, the more and more, exponentially more accurate the sensors have to be. Here's a little note that I think is a major confusion for people who are attracted to passive dynamics, is that people think that passive dynamics is efficient. So the muscles aren't on very much. It must be, oh, we want to make an efficient robot, let's make it passive dynamic. It's actually wrong reasoning. So here's a sort of an example with a simple model. The simple model of walking is that it's a point mass with legs that are controlled, light legs which are controlled. And where energy goes in a robot is to make up for energy that's lost. In the simple models, energy is all lost in collisions. That's when your foot hits the ground. In this model, here's showing the velocity vector of the center of mass swinging in a circle here just when the foot hits the ground. And then afterwards, it has to end up going up at sort of the same speed. In passive dynamics, you go bang. You have a big force along this foot that hits the ground, and you jump over to a new velocity here, and you lose this much velocity. And I know that velocity energy scales quadratically with velocity, but if you're looking at deviations, energy scales linearly with velocity, at least for small deviations. So you lose a lot. If you have to make that up somehow. And this is this 5-degree slope. This is the gravity energy that has to be made up in passive dynamic walking. If instead, just before the collision, you push off with this foot, you can move up to this state, and then you have a collision like this. And that collision can be 4 times smaller in energy loss. And the measure of how much energy loss you have is how far you move from this constant energy surface. And this line here is about 4 times smaller than this line here. The deviation goes approximately quadratically with the angle because a circle is about a parabola. And if you have half the angle, you have a quarter of the energy loss. So that means passive dynamics, compared to what we can do ideally, is a factor of 4 less efficient. It's not just a little less efficient, it's a factor of 4. So saying, oh, passive dynamics is a gold standard for efficiency or energy effectiveness is not correct. Okay, so what's the idea? Is put power and control all over the place. I think maybe following the biological analog. But I think we want to keep some of our philosophy, which is you want to keep things manageable. So you want to take passive dynamics and morph it into the world of power. And you say, how can you morph it into the world of power? Because passive dynamics is no power. It's you want to keep the idea of doing something in some simple and primitive way and put it into a place where you have lots of power and lots of sensors. So our test bed for this whole concept is now a stupid and boring robot, basically, which is because you'll see a video of it. But it's got, maybe I'll just jump to the video and show you what I mean by a stupid and boring robot. Pranav, are you here? Sorry. No, I think maybe he agrees. So here is someplace this robot that we made, which is sort of our answer to passive dynamics, or the first step in our trying to get beyond passive dynamics. This is trying to make a powered machine that is comfortable like people walking. So here's people walking, not afraid of them falling down. And the question is, can you be comfortable with a robot walking the same way? And this robot in this situation we were pretty comfortable with. So this robot compared to, say, Steve, so this robot was largely, at least the control system, designed by Pranav, who's back there. Do you want to just, okay. This robot, instead of having one teeny computer, has 6 decent-sized computers in it. And instead of running 60 lines of code, it's running something like 10,000 lines of code. And instead of having two 1-bit sensors, on-off switches on the feet, which the Collins robot has, this has about 25 analog sensors, or more or less analog sensors, 8 or 10 or 12 bits. The information flow here is about 100,000 times bigger than the one on the Collins robot. The computation is about 100,000 times more per second, like the number of lines of code executed per second. It's boring. It doesn't have knees. It doesn't even look three-dimensional. But this thing walked 65 kilometers without being touched or recharged, which is by far, I believe, and no one has challenged this, the record for walking robots. So it's 40 miles. That's twice what the Boston Dynamics people are advertising they're going to be able to do.
That's on a single charge?
Single charge, 40 miles. Nobody touched it for even 1 second. It's autonomous in that all of the walking control is on board. The lack of autonomy is this model airplane, $70 model airplane radio control for the steering. The motors on it are hip motor and 2 ankle motors. Outer ankles are one motor, inner ankles are one motor, and a steering motor which twists the inner legs when the inner legs are in contact with the ground for steering. This thing lives also in simulation, as opposed to the Collins robot, which didn't. And we have a pretty faithful simulation, which I forgot to queue up. But you can see the robot walking next to computer graphics of the robot. They walk at the same frequency, step length, and so on. Yes?
How much power storage is there?
It's about 500 watt hours. So I think it's 5 or 6 batteries that are about a pound each, and each pound is about 100 watt hours. So it's 5 cents worth of electricity to go for 30 hours of walking. In this incarnation, it was 16 watts or something like that.
What was the cost of transport?
The cost of transport in this walk was 0.28, and Steve's robot was 0.2. And then after this walk, Pranav did some optimization in the control and got the cost of transport down to about 0.19, which might be a little bit less than Steve's robot. So it's 30 hours of us sitting around like this, right? I don't know if this is fun to watch or not fun to watch, but here it's about to stop. It stops in a sort of graceful way. There, it stopped. Okay. Without getting into the details, the red curve is what we got from computer optimization. The blue curve is what we did when we ran the robot, which is this idea of keeping it simple. So we have sort of a control algorithm which combines optimization of performance with an informal optimization of complexity. Here's what we got out of it. Okay, so now just morals towards the end of the talk. Why were we seduced by passive dynamics? Passive robots were stable, sort of. And I think in a way, we would have been ahead in our robot research if passive dynamic robots were not stable. Right? In terms of when we design this powered robot and make it work, we don't even pay attention to whether it's stable or not passively. We start with the controlled machine and understand how the controlled machine works with control. So it's not like this idea, you have to understand the plant first before you add the motors and controls. The plant here includes the motors and controls, and we try to understand that, and we don't even think about the passive dynamic stability. It's not even it's not in the brain anywhere. So, sorry. Then there's the problem that the passive dynamic robots walk a lot like people do. And again, that's some kind of coincidence that passive dynamic motions are close to energy optimal motions. And you say, well, of course they are, but I say, of course they're not, because I know this example that is off by a factor of 4. But nonetheless, it's true that an energy optimal solution will have the motors mostly off a lot of the time. And a passive dynamic solution has the motors off all of the time. So they look a lot the same a lot of the time. When you do use the motors, though, it makes a difference exactly when and how you use them. So we've changed our thought from thinking of good powered walking to being passive walking with a small amount of control added, to being good power walking is highly controlled and highly optimized, and then tuned up to be efficient. And this is, as Hartmut pointed out, is Hartmut here earlier today to me, is that this is how people think about motor control in humans. People learn in very stiff and tiring ways how to do things, and then they tune themselves up and figure out how to do things in an energy efficient way. If you, probably all of you, have been trained in some motor activity, like playing the piano or playing the violin or high jumping or swimming or diving or skiing or something, you've had some coach teach you, and inevitably, one of those coaches has said to you, relax. The example that was most striking to me was after the Olympics once, one of these guys, Carl Johnson or something, just ran the 100-yard dash, 100-meter dash, and got a gold medal. And you see the slow motion video, and it's like, you know, all the muscles of the world you can imagine, straining like crazy. And they asked him, how did it feel? He goes, it was great, I felt really relaxed. It's like, like, what do you mean? Well, I mean, it means he was like using the right muscles at the right time and not using muscles he didn't have to use. Okay, so the new approach, roughly speaking, is that you start with a good model. You figure out if that model can move in a way that doesn't use much energy. You find a simple way to describe that. So when you do the optimization with the model, you're doing optimal control, and you have to parameterize functions of time. You look for simple ways of parameterizing those functions of time. In this case, for our model, Pranav started with optimal control with something like 120 parameters, and we found a way to reduce that, meaning finding an approximate functions that only had like 20 free parameters in them. And then we did optimization with those parameters and reducing the complexity by something like a factor of, I don't know, what, 8 or 10 or something. The energy cost went up by about 10%. Then once you have that, then you want to add feedback. And I sort of think of what the feedback we like as reflexes, so I'm not quite so literal about it as maybe Hartmut is, because I'm thinking of it on a machine. But the basic control architecture is there's triggers and motor actions. Triggers and motor actions, and these are happening pretty intermittently, nothing like an approximation of continuous in time. So it's discrete control, not discrete in the sense that we've got a clock cycle and we're trying to do continuous control, but genuinely discrete control with only a few special times and sort of extended time actions. And then you try to design that feedback to be as simple as you can and to do the best job you can. I gave sort of a practice version of this talk at Cornell, and somebody goes, oh, don't feel so bad that you spend all that time. It's not so bad. That stuff you did with passive dynamics, that was okay. So, you know, in control, we have to learn about the plant, and you did at least learn about the plant. And I guess that's true. You know, by thinking about passive dynamics, we learned about the plant, so you can think about controlling it. I'd like to think we learned more than that. We probably learned a lot of sort of skills, like how to calculate the stability of limit cycles and things like that. But it's, you know, had we not misunderstood the Wright brothers right from the beginning, and had it been that passive dynamic walkers, it turned out that they couldn't be stable, they were a little bit unstable, would we have got to where we are faster? And actually, it's not clear to me that we would have. And the question is why wouldn't it have been faster? You could have skipped all this passive dynamic stuff. And I think it's just getting all the ideas in your head and getting all the skills assembled. You just have to sort of build things up. And we happened to take a path through passive dynamics. Had we jumped to powered chris Chris isn't here, so I could make fun of it. That hydraulic robot that's down there that's all powered and isn't still working after 5 years of stumbling around, we'd be like that. You'd be in over our heads immediately. So you have to, if you want to make progress, you have to find some reasonable path. Was that an unfair insult of the poor Sarkos road? You have to find some path where you can, grab handles and work your way up. But if you jump into just trying to power things all at once, it's hard going. Okay, so that's my talk. Yes, Professor Collins.
So you're thinking about why Osimo isn't kicking your butt in terms of energy use. It's just that the system's too complicated, or as you're thinking about why they aren't blowing out of the water more, has it evolved in other ways?
I actually do not know. I think it might be that we're the only ones who are trying to do this energy efficiency thing, and that if the people who were designing Osimo before every time they thought of a new trick, if the first thing they did was run a model and do optimal control calculations, my guess is they would get a giant improvement. So I used to think, oh, it's bad because they have big gear reduction and blah, blah, blah. I'm not sure about that at all anymore. I think it might be that they're not efficient just because they're not trying to, they're not think it's not.
So they could.
I don't know how good they could get, but one example is the Cheetah, the new MIT Cheetah. And I actually don't know whether they had energy optimization in their design loop or not. Does anybody know? But anyway, the new MIT Cheetah, it's on a tether, but it's I think it's comparable, to what we're trying to do. And their cost of transport is 0.58. So they're only off by a factor of 3. And so what's the difference? Maybe it's not a matter of doing things well, it's just a matter of not doing things badly. Now, if you say, what about the Boston Dynamics robots? They're constrained by their decision that they made in 1980 to use a particular brand of Moog valve that I think they're still using. And those Moog valves just dump high pressure oil whether you're using them or not. So they could tune the hell out of it and they'd still be using, they still have to run a 10 horsepower motor to keep that oil flowing. Now if they took that Petman and replaced it with decent electrical motors, well, what would happen? One thing is their whole infrastructure, they'd have to redevelop that whole thing about how to make the motors work and so on. And then after that, what would happen? Maybe it would be not that bad. I don't know. Especially if they put energy optimization in their design loop. Do you have any thoughts on what I just said?
Not a lot. I agree that the Boston Dynamics robots are pretty power hungry, all hydraulic, and I don't think. I mean, their push has always been how do we put more power on board, not how do we make it more efficient.
But I mean, given that they're using hydraulics, they don't have a lot of options. The fast hydraulic equipment is shunting large amounts of energy, not using it judiciously.
I don't think they could make them run electrically, at least not the same output power kind of level.
Well, not so dangerously. You've probably had Mark Rabert here, have you? Has he given? So if you see the outtakes, which he'll show in a setting like this, those robots are dangerous because they have all that power available. They can do wild, strong kicks. And what are those wild, strong kicks good for is that recovery from disturbances, and not necessarily even recovery from big disturbances. My sense is that part of their stability comes from the fact that they can partially make up from sensor and model errors by making corrections late in the process. In particular, a key thing in walking, remember bicycles steer to the right to keep from falling to the right. Well, robots and people keep from falling by putting their feet in the right place. And if you don't think your foot's quite in the right place, you as a human or our robots can't do much about it in the last tenth of a second, but they can because they have this 10 horsepower available to, or maybe 2 horsepower for each joint to move it around. Okay, should I stop? Questions? Or, I mean, the most fun part for me is this part, so I don't know if it's the most fun part for you, but.
Well, then don't stop.
What?
Then don't stop. Maybe somebody will ask a question.
Tell another joke.
I mean, the thing I say in class is, what question do you wish somebody else would ask? And now ask it.
Do you know of any application of this to other motions, like swimming, for instance?
First of all, I don't know anything about anything, so I don't know. But I think there's this question about how to do motor control. Well, in certain contexts, I think people know pretty well how to do motor control. So for anchored arm robots, people know how to do motor control. But how to do motor control of systems that are somewhat under-actuated. There may be some degrees of freedom you don't have explicit control over. So that would include walking and flying and swimming. I don't think people have a good, as far as I can tell, nobody has really a good handle on how to control those things. Like a way to think about it, a design procedure that's pretty likely to work if you have a given machine. Boston Dynamics, they make a robot, it's great to see it, so they know something. What could they plug in to make that work if it's swimming? What could we plug in for swimming or even a different walking robot? I say we're all sort of groping around. So my thought is that swimming, flying, and walking are basically all the same problem. I don't believe that the fruit fly flying and walking is faced with a fundamentally easier problem than we are in walking. And how to do that in a graceful, good way, we don't really know. Yes?
So why don't people think about walking on bumpy terrains? So I know the answer is it's hard. So why is it hard?
Well, look, we're doing. I was at an NSF panel, and I said, we've got to solve walking on the walking problem. The NSF guy said, no, people have been talking about that for years. We've got to make robots that hop and skip and jump and blah. I said, nobody's made a robot that can walk on perfectly level ground decently yet. Okay, they've been talking about it for years. So is walking on uneven terrain hard? I don't even know. I don't know if walking on level ground is hard. All I know is that none of us have done a good job of it yet. Might it be that walking on level ground is equally hard as walking on rough ground? I think that might be. So, if I want to say mistakes in our thinking, there's a community of people who've been all interested in limit cycles and stability of periodic motions and so on, which you have for level walking. On rough terrain, you certainly do not have that. But it is perfectly likely to me that a sensible controller of walking is planning 1 or 2 steps ahead, and is planning 1 or 2 steps ahead, whether it's on level ground or on rough ground. And there's really not a big difference. It's a little easier because you can run the same plan basically again, or the same set of reflexes, say again. But it's not clear to me that it's essentially harder. So I hate it when people go, oh, it's a hard problem. I mean, walking is, first line of paper, walking is an unsolved problem. It is very difficult because it's non-holonomic, intermittent contact, variable dimensional, under-actuated, nonlinear problem. It's not clear to me that it's any harder than swimming or flying or rough terrain. Well, that's true, but so sort of under-actuated, I would say. Non-holonomic isn't the key. It's sort of under-actuated, I feel like, is the key. Did I do a sufficiently good job of not answering your question?
Well played, sir.
Yes?
You said that you just need to make something, it's good to start with a model that's easily controllable, or I'm having trouble formulating this, but what are some of your metrics for easily controllable?
Okay, so let me just repeat what I said. The passive dynamics was enticing because we had a model which we could build and in computer simulation was self-stable all by itself. And you think, oh, that's a good place to start. Instead, I think all you need to start is a model that when you add the sensors and motors to it, you are able to control. And then there's a question of how able and how, so what do you mean by what makes easy? walking sort of has a step involved, maybe 2 steps. And then if you can do that, you can do lots of them. So long as nothing big as far as instability happens in that time span, I would call that easy to control. And if I could make an analogy with the bicycle, bicycles are self-stable only in a speed range. A given bicycle, maybe 8 to 12 miles an hour. When you're riding a bicycle, you feel like you're stable. You can ride it no hands. You can ride it no hands and blindfolded. If you're riding at the right speed, you can ride it no hands and blindfolded with your hands behind your back and a board strapped to you. But you're riding along. The bicycle feels kind of stable. When it goes very slow, you can sort of feel that it's unstable, and you have to do a lot to control it. But when it's going faster, you can sort of, that self-stability, you kind of feel that. And it goes faster still, and you still feel it. And actually, the bicycle's lost its self-stability. So when you get above a certain speed, the bicycle's no longer self-stable, but the characteristic time of that instability is very long, 1, 2, 3, 4 seconds. And meanwhile, you're avoiding potholes, staying on the right side of the road. You're doing things to steer and control in a shorter time scale. So long as the instabilities are long compared to the kind of control you want to do anyway, it doesn't matter if it's stable or unstable. So I think that's what I was talking about. When I said easy, I just meant that there's not so much instability going on that it's hard to keep up. Like with a bicycle going 1 mile an hour, that's hard. Yes?
So in your thoughts on passive actuation, have you thought about like series compliance or variable compliance and how that factors into?
Yeah, well, I have abstract thoughts. So I got into the business of robotics by seeing a talk by Mark Rabert on his hopping robots, and I thought, he's got these artificial animals that are like dogs and so on, and they're using 10 horsepower, and horses are using. So something's wrong here, and my first thought was springs. And I started an email correspondence with him about springs, and you should make it all happen naturally, and he said, you should meet Tad McGeer, and then he invited Tad McGeer to his lab, and I met Tad McGeer, and so on. So I used to think in terms of springs and sort of passive mechanisms to increase efficiency, and I don't actually think about those at all anymore. And I find it mildly annoying when people say, oh, we're going to make an energy effective robot because we're going to put a spring here or there, because look, we didn't put any intentional springs in this machine at all. And we basically just tried to build a reliable, sensible machine, and it's 10 or 100 times, uses 10 or 100 times less energy than other robots. Now, once we got really good, obviously, if you do things with springs in the right places, you can get more energy effective. In the end, there's a factor of 2 or 3 you can get with springs. But we're talking about factors of 10 just by not doing stupid things with control. So I think people festering on springs, for example, series elastic actuators, they're sort of off the mark in terms of, for us, understanding basically reasonably energy effective locomotion. Now, of course, there are counterexamples, like these guys built a very good hopping robot with springs. But most of the people, that's refined product. Most of the people putting springs in are building clunky robots like this and adding series elastic motors. I don't know if you know his thing, but. Yes?
So I'm curious about your thoughts about a skiing robot.
Yes.
In particular, the scaling issues, because grown-ups have to ski with poles, but little kids ski without poles.
I think I could fill the room with sound waves in response to that question, but I might not say anything sensible. So I have no quick thoughts on that. You know, there's scaling issues having to do with energy, and there's scaling issues having to do with stability. And the stability ones would seem to me work backwards from what you said, in that it's easier to balance a broomstick than a pencil. So I don't. If you're right in what you said, I don't have any simple explanation for it. Yes?
Yeah, so I have a question. Given sufficiently good controls, would it actually make better walking robots if we have more articulated joints?
Well, better in what way?
So like, which would handle, deflections or instability that, if you push it in a transit direction.
Okay, let's take our robot here has no knees. Okay, how come the feet aren't hitting the floor each time they swing? Because we have a little ankle on our robot that twists out of the way so it can clear the ground by about 1 centimeter. No matter what control we put on our robot, if you give it a 1.5 centimeter bump, it's going to fall down. So knees are obviously useful for large obstacles if you had a sufficiently good control. There's no question about that. Knees are obviously useful for saving energy because it's easier to swing a double pendulum like a kneed thing than a straight leg thing. Right now, with this robot, we're not taking advantage of those things. In our next robot, which I hope we get money for someday, we will add knees, but not for the purpose of making it more robust, but just to make it look more cool in videos.
Well, I think we should thank our speaker once again. And I'm sorry to cut you off.
Ah, it's all right.
Your fun
I know,
yeah.
yeah.
Thanks, that was fun.
Thank you. Thank you. I probably have like 5 minutes for questions up here, right? Do I have a few minutes here? I don't know.
Oh, you can stay here. He's going to hang on for another 5 minutes, so you should just like gang up. So that's very thought-provoking. I'm